Hello, everyone, and welcome back to your channel uh, of basic engineering, but now we are doing probability and statistics. And as I promised, today we are going to start with the most important distribution or continuous distribution in statistics, quality control, reliability, and you name it. And it's called the normal distribution or the Gaussian distribution. Okay, so the probability mass function, the probability density function of the normal distribution is as follows. 1 over the square root of 2 pi times sigma times e raised to the negative x minus mu. And this is over 2. So I prefer to write it like that. Square over 2 sigma square. Some people write it as 1 over 2 pi sigma e to the negative 1/2, and then between parentheses, which I prefer, x minus mu over sigma, and you will see why in a second. Wow. So here we don't say that mu equals 1 over something or sigma. No, mu and sigma, you provide them. And based on that, you get the distribution. But no matter what mu is and what sigma is, this distribution, as you know, is like we call it the inverted bell curve. And it's very important because it models a lot of physical processes. Not only that, you will learn this when we go into the linear combination of random variables. It's very nice and very easy topic. But we are saying here that if I have a random variable coming from a particular distribution, like the exponential distribution, okay, that's the one we know of, or even um, the uniform distribution. The exponential is hard enough because the exponential is not symmetric, but the uniform is. If it's uniform, it's easy, but if it's not uniform, I will explain that in a second. If I keep taking samples, meaning, let's say I take, let's make it a nice square. So 9 units of an exponential distribution today, and I calculate their average, the mean. And then I take notice that when you calculate the mean, you will not get exactly 1 over lambda, right? Because that's random. Every day you can pick different numbers. So tomorrow I pick the day after. I keep doing that, and then I draw the distribution of the means, not the distribution of the individual units, the means. If the sample is large enough, let's say 30 or 40 units instead of 9 that I said, so 36, for example, every day, and I calculate the mean, and then I draw a histogram of the mean, okay, I will get something that resembles the normal distribution. That's why it's very powerful. It's that on the limit, when you take large samples from any distribution, well, not any, 99% of the distributions known to us, and find the mean or the total for that matter, and you draw a histogram of those, they will look like that. Say, why? It's not normal. It's exponential. It's Weibull. It's log normal. Why does it become normal? We'll cover that later. Excuse me. So now when I try to find the cumulative of this function, that's very tough. Because when you try to integrate this function, you can get it into a closed form solution. It's not like the exponential when I say 1 minus e to the negative lambda t. No, there is no such thing. So it's really hard to do. So mathematicians in the past thought of making a table for the normal distribution, but they were faced with a problem. It's impossible. Why is it impossible? Because every time you change mu or sigma, I'm sorry, mu or sigma or both, you have to create a new table. So what do we do? What to the rescue? Substitution. Yes, substitution. So they said, okay, we are going to create only one table. And this table, instead of using x, mu, and sigma, we are going to combine mu and sigma with x into something new. And since this is the one posing the problem when you integrate, we are going to replace it with something called z. And z is x minus mu over sigma. Notice what happens when you subtract mu. So here is mu, right? It's symmetric. So this is the mean, this is the median, this is the mode, this is mu. And do you see the inflection point here? The distance between the mean and the inflection point is sigma. And this is the x-axis, right? But they said, see how clever they were. They said, okay, any x here, if I want to find the cumulative of any x, it would be easy if mu was the origin, meaning this distribution is centered at 0. It has half of it to the right of 0 and half of it as negative to the left of 0. They said, okay, but we didn't fix the problem with sigma. I said, okay, let's make sigma equals 1. So mu equals 0 and sigma equals 1. So if I have another axis here, call it the z-axis, that would be 0. This number is 1. This number is -1. And then you can go 2 and -2, 3 and -3, and so on and so forth. Okay? But how do I do that? First of all, I need to subtract. If I want this to be 0, so I'm going to subtract mu from any x. So I say x minus mu. So that becomes the 0, but now I have sigma. So shrink the whole thing by dividing by sigma, and that becomes 1. Do you see? So here if I substitute and I say at x equals mu, z equals mu minus mu over 0, so over sigma, so I get 0. If x equals mu plus sigma, this is mu plus sigma, then z becomes mu plus sigma minus mu over sigma. These cancel and you get 1. Yes. -1, and so on and so forth. So think of it like that. If on the x-axis we are moving 1 unit to the right or to the left, here we move 1 sigma to the right or to the left. Okay? So now when this is the case, and you substitute in the function, so in the cumulative, which we don't know, and take the derivative, at the end of the day, you get phi of x, I'm sorry, of z equals 1 over, I think we usually use phi for the cumulative, so don't use that. Let's say f of z becomes 1 over the square root of 2 pi. Notice because when we say if z equals x minus mu over sigma, like we did in integration in substitution, then the dz would become 1 over sigma. When you take the derivative with respect to x, right? So you get, this is dx over sigma, and the mu is 0. So you replace dx over sigma, which here when you take the integral, it would be integral with respect to dx over sigma. That becomes just dz. So there's no sigma here. We got rid of the sigma by taking that change, and this would be negative 1/2 z squared. And that becomes very powerful because now I don't care what your mu or sigma is. Just substitute, make that transformation to standardize it, and that is become the standard normal distribution. And now they were able to create tables for z. And then if you have a different mu and sigma and you got, say, a z of 2, you say, okay, so x is 2 sigma plus mu, right? You solve for x. It's very simple. Of course, nowadays you don't need to do any of that. You have calculators, you have computers, so you can find that cumulative distribution, which is the integral from negative infinity to plus infinity of f of z dz. You get that from tables. So what we are going to use is a standard normal distribution that has a mean of 0 and a standard deviation of 1, regardless of your mean and standard deviation. So let's take an example. Suppose I have a distribution, a normal distribution with a mean, let's say, of 300 units and sigma of 50 units. And I want to find the probability that x is greater than whatever, 280 and less than 335, anything, okay? So I would say this is the same as saying I would subtract the mean and divide by sigma for both sides. So that's the probability of, now if I subtract mu and divide by sigma, it becomes z, that z is greater than, less than. 280 minus 300 is negative 20, over 50 is negative 0.4, and 335 minus 300 is 35, divided by 50 is 0.7. So that is the cumulative of 0.7, because 0.7 is somewhere here, minus the cumulative of negative 0.4, where negative 0.4 is somewhere there. So I want to find this area. So you go and take the table and find the cumulative of negative 0.4, and you subtract from it the cumulative of 0.7, and you subtract from it the cumulative of negative 0.4. Okay? Calculators can do it, computers can do it, and it's so easy. Okay, so now it becomes, we can look at some like properties of the standard normal distribution. So let's draw it again here. Here is the standard normal distribution. Here is the 0. Here is the 1. And here is the negative 1. So we say the area under the curve, we know it's 1. But we know that the cumulative between negative 1 and 1, meaning the cumulative of 1 minus the cumulative of negative 1, is roughly 68.3%. So almost 60 or 68% of the distribution is close to the mean. If you take it from 2 to negative 2, you get roughly 94.5. And if you take it from 3 to negative 3, which usually in the past, especially most technologies were assumed that this is the whole distribution because it's 0.973, 97.3% between plus or minus 3 sigma. So these numbers are very, known and used in industry. You might have heard me talking about an initiative that started by Motorola and then GE adopted it, which is called the Six Sigma. Uh, that's hard to explain now that because we are talking about, I might have told you that as if you work in quality control, your most ardent enemy is sigma. You want to reduce sigma as much as you can. So they would say, okay, if I have specification limits, meaning my customer will not accept anything outside of this range, I want this range to equal 6 sigma of the process. My process should be very close to the mean. In fact, theoretically speaking, if you reach 6 sigma, you you can you can have a process that almost is uniform. Everything is between these two. It's very, very close, but again, I don't want to go into that, but you can think of it. I mean, if you use your calculator and find the cumulative, um, so if you see what's outside the specification limit, we'll talk about that on another day. Okay, but having said that, now I can tell you, suppose, okay, I want to say, for example, suppose I have a point here at, say, negative 1.2, and I want to find the area or the probability that I get a number from, or a random variable, my random variable from this distribution is higher than that. So it's to the right of that. How do I calculate it? Do you see I can take the cumulative of negative 1.2 and then subtract it from 1. So I say it's this area right here is 1 minus the cumulative of negative 1.2. Okay? What if I have to find the area to the right of 1.2? This area. So I'm using the pencil to distinguish it from that total area. How do I find this area? Well, it's not drawn to scale, but you notice that because the symmetry of the distribution, the area to the right of 1.2 is exactly the same as the area to the left of negative 1.2. So one property is that the 1 minus the cumulative of any value of z equals the cumulative of negative z. And that becomes easy instead of people finding the cumulative of 1.2 and then say 1 minus that and get it. No, it's just the cumulative of negative 1.2. Okay? Um, I don't think we have much to say about that for now, but we have a lot of applications to the normal distribution that we may start dealing with in the next sessions. In fact, even before doing that, I want to introduce the topic of the linear combination of random variables because it makes life much more easier for you to understand as we go from here and start delving into statistics. Because we are not going to cover, well, we will cover some material that is in probability to help us understand what's coming in statistics, if that makes sense. Because basically the probability is the basis. That's the model that you will be using. And then the statistics is like the practical application of probability, if you want to give it that name. Okay, so I think that should be a short one. I'm going to stop here and we will continue later. Thanks for your watching and hope to see you soon. Have a great day.